So this is the second stochastic modeling lecture. Last time we talked about Monte Carlo simulation from univariate and multivariate probability distributions. We talked about other related concepts in stochastic modeling using Monte Carlo, specifically the law of large numbers, the central limit theorem, and we ended up talking a little bit about bootstrapping as well as a time series modeling approach. Today we're going to talk about Markov chains, which are sort of related in a lot of ways to our discussion of joint probability distributions or conditional probability, but are sort of a distinct approach for modeling different types of stochastic processes. And so that's what we're going to do today. So I think it would be useful to watch this Khan Academy video on Markov chains before watching the rest of this video. So take a minute, watch that video, and then come back to this and finish. So a Markov chain is a random process. It's a stochastic process. And it's one that specifically undergoes transitions from one discrete state to another in a given state space. So a state space means the number of possible values that a certain process could have. And in this case, not only are you going from different values, one value to the next, but the probability that you move from one value to the next is determined by a specific distribution that's tied to the current state that you're in. And so a specific property that's unique to Markov chains, or not unique to Markov chains, but is required for a process to be considered a Markov chain, is what we call memorylessness. And so this should immediately strike you as something that's different than how we've thought of time series processes in the past when we're talking about autocorrelation, where the value of some sort of process tomorrow can depend on the value today and yesterday and several days before that. In this specific context, what we call memorylessness means that the probability distribution of the next state, a future state, one period away, depends only on the state that we're in right now, and not on the sequence of events that have preceded it. So that's a pretty abstract concept, but I think it will become clearer as we go through this lecture. So this is a more formal way of laying out this property of memorylessness for Markov chains, and we specifically call this the Markov property. And so we're dealing with a discrete time process, right? And so all that means is that we have some variable x that potentially could have a different value in each period n, each time period n. So x is a variable that has a different time value potentially in each period n, where we can say n can go from 0 to 1 to 2, etc., all the way up to whatever time duration we're talking about. And this process, xn, has a discrete state space, right? And so the state space, think back to when we're talking about the probability of a deck of cards or rolling dice. The state space are all the different possible values that this xn could take, right? And we're specifically saying that no matter what period it is, no matter what n value we're talking about, the value of x can be 0, 1, 2, etc., and we're predefining what the possible values of x can take here. And we would call this discrete time process a Markov chain if it has the so-called Markov property. And what the Markov property says is that the probability that xn plus 1 equals j right here, the probability that the x in the next time period equals some value j, given the fact that in the current time period x equals I, and then in all previous time periods, x has had all these other discrete values, is simply equal to the probability that x in the next period equals j, given the fact that in the current period x equals I. So this is a fancy way of saying that all this stuff doesn't matter, right? That it doesn't actually change the probability that in the next time period we have a certain value of x. All that matters is what the current value of x is. That's what defines the probability of x becoming any value in the next time period. So informally, in words, we would say that the past is conditionally independent of the future given the present state of the process, or given the present state, the past contains no additional information on the future evolution of the system. Now think down here, how does this differ directly from autoregressive modeling? And the answer here is that autoregressive modeling, potentially we're looking way into the past, several periods into the past, to get useful information that describe what the probability in some cases are or is of the process x being a certain value in the future. So here's an example of what we call a simple two-state Markov chain. Two states means that our process, you could think of x being the underlying process, the state space is only has two elements in it, right? There's two possible values of our x variable, right? The first is e and the other is a. And so our process can bounce around between these two states through a conditional random process, which means you're drawing from a probability distribution, and depending on what that value is, you can move from e to a and a to e, but depending on what state you're in, e versus a, the probability of staying in the current state or moving changes. So for example, if you're in state e, so if x has the value, or is associated with the value e, then you're essentially saying that you're reaching into a bag that has 30% black marbles and 70% blue marbles. And if you get a black marble, you stay at state E in the next time period. If you get a blue marble, then you move to state A, right? So this isn't, it's hard to think about that as a distribution that has a shape that's normal or anything like that. You're just talking about the probability of staying in state E or staying in state A, and we're equating that to reaching into a bag that has a certain number of marbles of each color. And in this case, clearly, if you are in state E, it's most likely in the next time period you're going to be in state A because you have a higher probability of reaching in and getting that, hypothetical blue marble. Now, it's different if you're in state A down here. Then what we're assuming here is that what determines where you are in the next time period, again, is what you get when you're reaching into a bag that has marbles, and it depends on whether you get a black marble E or a blue marble A. But in this case, the probabilities are different. So we're saying that if you are currently in state A, then you have a 40% chance of moving back to state E, and you have a 60% chance of staying in state A. So another way that you can express this is just as conditional or dependent probabilities. And this is something we talked about towards the beginning of the year when we were talking about probability and descriptive statistics. So let's say, and we're not talking about, let's talk about a random process being represented by the letter y, right? That's our random process. And what y represents here is the next system state, right? So what the value of this process is going to be in the next time period. And we're going to denote x here as the current state. We could equally describe this system using, y being the random process and y minus 1 being the current state or something like that. Or we could say the current state is y and the future state is y plus 1, or y t plus 1 or n plus 1. But in this case, we're saying y is the future state, x is the current state. And so we can look at this figure and basically say, all right, what's the conditional probability that the future state is E, given the fact that our current state is E, right? So in other words, what's the probability that if you're currently in E, or what's the probability that you end up in the next time period in state E, given the fact that you're already there, right? And that's clearly this one, right? And visually, that's what this describes. You're moving from E along this arrow, and you're just going right back. And so that's the conditional probability of in the next time period being in state E, given the fact that in the current time period you're already in state E, and that's the probability of 30%. We can do the same thing trying to figure out what's the probability that in a future state we're in E, given the fact that currently we're in state A. And so that would look like this one, right? If we're currently in state A, then we have a 40% chance of ending up in state E next time. Same goes with this. If we want to know what the probability of ending up in state A is in the next time period, given the fact that we're currently in state E, then we just look visually at what arrow is going from E to A, and that gives us information that we have a 70% chance of ending up in state A if we're currently in state E. And the last one here is what's the probability of being in a future state A if we're already there, and that's a 60% chance. So this way of denoting conditional probability or dependent probability should be somewhat familiar to you. And this is, we're directly interpreting this two-state Markov chain, this visual diagram, in terms of conditional probability here. So another way of succinctly describing that exact same information is using what we call a transition matrix. And so this is a way of organizing the conditional or dependent probabilities that describe the random process. And so we have the same information that we just gleaned from the visual picture, right? Describing the probability of ending up in a future state. We're in a two-state system where you can either be in state E or state A, and we're thinking right now about looking at what the future state Y is, really. And so we figured out what the probability is of ending up in the next time period, Y, in either one of these states, E or A, based on what we are currently in. And so we can organize that same information in this matrix down here, where on the y-axis tells us where we are on the y-axis, tells us whether we're currently in state A or currently in state E. And based on that information, it gives us the probability that we then end up in state A or state E in the next period. So for example, if we're in state E, then we have a 30% probability of staying in state E in the next time period. If we're in state A currently, then we have a 60% chance of staying in state A, right? And then the off diagonal, this stuff gives you information about what the probability is of jumping from E to A or from A to E. So a famous Markov chain is called the Drunkard's walk. And this is a random walk, which you should be a little bit familiar with. We talked about a random walk just being a process that is not autocorrelated at all, right? It's just saying that the value tomorrow equals the value today plus some random sample from a Gaussian distribution, right? And we're sort of saying the same thing here. So our drunkard's walk in this case is a random walk on the number line, where at each step the position can go +1 or -1 with equal probability, right? So in other words, you can go forwards. You have at every time period, you have a 50% chance of going forward. You have a 50% chance of going back, right? So at any position, there are two possible transitions, going forward or back. And if we're talking about a number line here, we're talking about integer movements, so going from 1 to 2, 2 to 3, or going backwards from 3 to 2, 2 to 1, etc. So, for example, the transition probabilities for each of those movements from 3 to 2 and from 3 to 4 are both 50%. And all other transition probabilities from 3 are 0. In other words, you cannot go from 3 to 1, and you cannot go from, say, 3 to 5 or something like that. You can only go from 3 to 4 or 3 to 2. And then, however long we want this number line to be, we have endpoints. And in this case, our endpoints are at 0 down here and at 4. And the rule here is that once you get to an endpoint, the probability of moving away from the endpoint is 0. So once you get to an endpoint, there's a 100% probability every time of staying there and a 0% probability of moving. So we can sort of go through a similar series of steps converting this visual diagram here to conditional probabilities to a transition matrix here. And so let's do that. So what the visual diagram shows is that, for example, if you're at state 2 currently, then you have a 50% chance of going to state 1, and you have a 50% chance of going to state 3. And we can sort of look at that in the probability in the transition matrix. So remember, on the y-axis, this describes what the current state is. And on the x-axis, the columns describe what the future state is. And so if we are in the current state is 2, then we know we have a 50% chance of going to state 1, which is this 1 column up here. And we have a 50% chance of ending up in the next time period at state 3. And we have a 0% chance of going from 2 to 0. And we have a 0% chance of going from 2 to 2. So you cannot stay at the same place unless you're at an endpoint. And you have a 0% chance of going from 2 to 4. And you can go row by row and sort of visually convince yourself that this transition matrix represents the diagram that we have up here, including our endpoints up here, right? So if you're at 0, which is the first endpoint, then you have a 100% probability of staying at 0 and a 0% chance of going anywhere else. And this has a special name for certain states like this. Same goes on the bottom here. You have a 0% chance, if you're currently at state 4, of moving at all. You have a 100% chance of staying at state 4. So the special name for the endpoints here, 0 and 4, are called absorbing states. That means that whenever the process ends up on a 0 or 4, it gets stuck there. And we can easily identify absorbing states in the transition matrix by diagonal elements with the 1s here, a 100% probability. That means there's no chance that if you're in one of those states, 0, 4, that anything else happens other than you just stay there. So far we've looked at two-state Markov chains where there's only two possible states of the world. Of course, you can go well beyond that as well. So this is an example here of a three-state Markov chain with no absorbing states. In other words, you never get to a state where there's a 0% chance of moving away from that state. So the process is never getting stuck at some sort of endpoint here. And so in this case, we're talking about the stock market, and there's three different states, right? There's a bull market, which means in general the market's going up. There's a bear market, in other words, so the market's going down. And then there's a stagnant market in which things aren't changing much at all. And so visually here we can interpret all the lines going from one state to the other and from one state to the current state as being the specific transition probability. So if we look just at the bull market first, right? So we're just doing the bull market. It has a 7.5% chance of going from a bull market, so a good stock market, growing stock market, to a bear market. It has a 90% chance of staying in a bull market, and it has a 2.5% chance of going from a bull market to a stagnant market. Right? So if you're at a bull market, there's three different possibilities. You go to a bear market, you go to a stagnant market, or you stay in a bull market. And overwhelmingly here, we're saying that the most likely outcome if you're currently in a bull market is to stay in a bull market. We can look at the same thing for a bear market. So if you're currently in a bear market, then you have an 80% chance of staying in the bear market. You have a 5% chance of going to a stagnant market, and you have a 15% chance of going to a bull market. And last, if you're currently in a stagnant market, then you have a 50% chance of staying there. You have a 25% chance of going to a bear market, and you have a 25% chance of going to a bull market. And we can again convert this visual interpretation into a transition matrix, where again each row describes what the current state is, and then each column describes what the next future state is. So if we wanted to say, what if we're in, well, I guess we should determine here which rows are which. Here it looks like number 1 here, number 2, number 3 is equivalent to bull, bear, and stagnant. So this is bull. Oh, it's painful to write here. That first row is bull, second is stagnant, and no, second is bear. Bear, God, that's awful. And then the third is stagnant. Yes. So the one I circled, the probability that a bear market stays in a bear market is 0.8, and so we can visually go back up to the graph and verify, yes, that if you're in a bear market, you have an 80% chance of staying there. So we can use transition matrices to make predictive statements about the system we're modeling, particularly predictive statements about things that happen in the future. And it doesn't have to just be the next time period. Even though our transition matrices are explicitly describing what the probability is from going from a current state to a state one period into the future, we can actually use them to make predictive statements for time periods more than one period away. That can be a little complicated, and I want to walk through an example here. Now, just one thing to keep in mind, you may be wondering, or may not be wondering, how you would sort of build a transition matrix. And so a lot of that would come from historical data. In other words, if we're talking about a three-state system describing the stock market, where it could be a bear market, a bull market, or a bull market, a bear market, or a stagnant market, we could go through the historical record and look at every single time the stock market was in a bull market. What's the probability that it stays there? and we could figure that out just from empirical data or sample data. Same goes as, we could figure out what the probability is historically of a bear market going from a bear market to a bull market, or a bear market to a stagnant market, right? And so we could build empirically these transition matrices. Now, one thing to keep in mind then, that any prediction you make about the future that's based on a transition matrix that you built with historical data in the past means that you are fundamentally assuming that the dynamics of the system that yield these different probabilities of the system moving from one state to the next are staying the same in the future, right? So in other words, the future is going to look something like the past. So we've talked about why that can be a good assumption. We've talked about why that can be a bad assumption. But what the main point here is that you need to know that that's an assumption, and it's really important. So let's go through this example. So we can describe the probability of being in each state using a row vector xn. So, and this is a little silly, just sort of a naming convention. But let's say we have this row vector xn, and that describes the probability of being in each state. And so if we are in week n now, right, and we know that the current state of the system is 2, so a bear market, then we can say with 100% probability or certainty that the probability of being in state 2 is 1, right? And there's a 0% chance that we're in a bull market or a stagnant market, right? And that's a little trivial, right? Because we're not making any predictive estimate here, because we are saying what's the probability of being in each state in week n, given that we're already in week n and we already know what the state of the system is. But what I want you to sort of get here is the how we're using this naming convention, where we have xn and the probability is a vector, and each element of the vector is the probability of the system being in each state. So if we're in week n now, the probability of being in each state in the next week, xn plus 1, is then this other row vector, right? And that's a vector, xn plus 1, x to the n plus 1. And we calculate the values in that row vector by taking our current vector, row vector, that describes the probability of being in each state of the system in week n, given that we're already there, times. So we can keep going with this. So actually, we can define 3 weeks later, if we want to know what the probability of being in each state is 3 weeks from now, right? We can actually determine that using the current state of the system and the probability matrix, the transition matrix alone. So here we're saying that we have this row vector x to the n plus 3, which we're going to say that's what holds the information about the probability of being in each state in the future. And similar to how we saw on the previous slide, we know that that row vector is described by the row vector describing the probability of that state, of being in each state in the previous time period, times the transition matrix, P. Right? And we can similarly say, okay, well, we can break up this row vector describing the information in period n plus 2 into what we saw before. The row vector here containing the information about the probability of being in each state in time period n plus 1 times the transition matrix. And then we can break that down even again into, again, the row vector with the probability of being in each state in time period n times the transition matrix, right? So in other words, we can describe the probability of being in each state 3 periods into the future purely as a function of the transition matrix and the row vector with information about what state we're in right now, right? And so this x to the n is a row matrix, or row vector, and then we have the transition matrix here cubed, right? And so you have to do some matrix multiplication here, but eventually you can multiply the matrix times itself 3 times, which yields this new matrix, and then you're multiplying a 1 by 3 matrix times a 3 by 1 or 3 by 3 matrix, and you do matrix multiplication again, and you end up here with another row vector which describes the probability of being in each state in the future, given the fact that in your current state you are in a bear market, right? So given the fact that we're here, that we're in a bear market in state 2, we have a 50% chance of being 3 weeks from now also in a bear market. We have a 7% chance of being in a stagnant market, and we have a 36% chance of being in a bull market. So you could imagine that if we can do this for 3 weeks, right? If we can figure out what the probabilities of being in each of these 3 market states is in 3 weeks, given the current state and the transition matrix, there's no reason why we couldn't do it for 4 weeks or 5 weeks or 10 weeks or 2 years, right? And so you can take this same approach basically and use the transition matrix to calculate the long-term fraction of weeks during which the market is stagnant, or the average number of weeks it will take to go from a stagnant to a bull market, right? You can figure out the steady state probabilities of each type of market condition, right? The probability of being in a certain market, basically regardless of the current state. So the reason why the current state eventually doesn't matter is because if you're including more and more of these time periods, if you're looking out further and further into the future over more and more time periods, the current state of the market ends up not really mattering, right? And so formally what we're really saying here is we're trying to figure out the row vector that it doesn't tell us about the probability of being in a certain state, in 1 period or 2 period, but basically as n goes to infinity, right? And so if you take n to infinity, what you're basically doing is multiplying the current state times sort of an infinite number of different transition matrices, where you're multiplying them over and over again. And eventually, those numbers converge to steady state or equilibrium probabilities. Okay, so if what we're doing is trying to figure out the long-term equilibrium probability of being in each state, what we're really saying is we're going to define that as a row vector q, similar to the row vector x to the n, or x to the n plus 1, or x to the n plus 2, except we're saying that q is x to the n when n is going towards infinity, right? And that should give you some idea of how you would sort of approach calculating that. Like you could say n is 100, n is 1,000. What you're really doing is taking that initial state vector x to the n, and multiplying it by additional transition matrices. You're just multiplying the transition matrix by itself more and more times. And so one of the unique sort of mathematical qualities that we're going to say here is, if we're talking about the equilibrium probability, what that means is that over the long term, the probability of being in any of these states of the world, whether it's a bear market or a bull market or a stagnant market, is independent from where we are now, right? So where we are doesn't matter. If we're talking about the long-term probability of being in one of these market states, then where we are doesn't matter. And if where we are doesn't matter, right? If the values of this Q row vector are independent of the current state, then fundamentally, and requires a bit of a leap of faith, it must be unchanged when it's being transformed by P. Right? Because if it was changed by multiplying another probability or transition matrix, then we would not have reached the equilibrium state yet, right? So Q has to be something that is unaffected by multiplying it times yet another transition matrix, right? And so this mathematical property, that if you're multiplying the row vector Q times P, the transition matrix, just gives you Q again, that means that Q is what we call an eigenvector. You can look that up. If you've already taken linear algebra, you might know what that is. If you haven't, then you would learn this in linear algebra, or you could go look it up on Wikipedia. But we can derive that then from P, the transition probability matrix. So for the stock market example, we know what P is, right? This is the transition probability matrix that we've already calculated from that figure. And so what we're saying here is that if Q is truly the vector of equilibrium probabilities, then if we're just multiplying it by one transition matrix, we would just get Q back. Otherwise, if this weren't the case, then Q fundamentally would not be the equilibrium probabilities. And so we can also say that, again, from linear algebra, we know that multiplying a vector times the identity matrix, and the identity matrix is over here, it's just a matrix with ones on the diagonals and zeros on the off diagonal. Multiplying a vector by the identity matrix just gives itself, right? And so QP equals Q is the exact same thing as QP is equal to Q times the I, the identity matrix. And so if we have QP is equal to QI, we can say QP minus QI equals 0. And then we can pull Q out of that equation to get this equality here. So we're saying Q is times P minus I is equal to 0. And then we can actually do some arithmetic here and subtract the identity matrix from P. And this is still, here we have, this is equal to 0. So 0 is equal to Q times P minus I here, and this is P. This is our original transition matrix, and this is the identity matrix. So if you're with me here, we have P minus I in brackets times Q, which is what we're solving for. Remember, Q is the equilibrium probabilities. That simplifies to this. And then we have, we can break Q out into these three values. So Q1 would be the long-term probability of being in a bull market. Q2 would be the long-term probability of being in a bear market. And Q3 would be the long-term probability of being in a stagnant market. So here we have a 1 by 3 vector times a 3 by 3 matrix. And we can multiply these out and we get a system of equations, or three equations and three unknowns, and of course 0 is on the other side here. That's what allows us to set all these equations. And if you're wondering specifically how I got these three equations by multiplying this vector and this matrix together, that's again linear algebra. And the other thing we know here is that these three all add up to 1, right? We know that the long-term probability of being in a bull, bear, and stagnant market all have to add up to 1, because those are the three possible states of the world. So we have this system of equations with three unknowns, and we can actually solve for this. And so using these three equations and these three unknowns, we can solve for Q1, Q2, and Q3. And so that means that the long-term probability of being in a bull market is about 63%. The long-term probability of being in a bear market is about 31%, and the long-term probability of being in a stagnant market is about 6%. And it has nothing to do with what the current state of the system is. It all has to do with the transition matrix, right? But remember, the transition matrix is something that we calculated from historical data, right? And so we're basically saying that in the future, the probability of being in a bull market depends entirely on the probability of being in a bull market in the past. And so that is the fundamental assumption and sort of weakness of this type of approach. So here's another concrete example of a Markov chain, from finance. And so this comes from a really famous textbook on options and derivatives. So this isn't my text up here. This is all from a textbook, right? So of course it's not a homework. There's no homework in this class really. But what this shows are transition probabilities from rating agencies, right? So just a little bit of background. If you are a corporation or a utility, public utility, or anybody that's borrowing money, right? You have a credit rating. We all have credit ratings, sort of. We have credit scores, right? And this is similar. And your credit score determines what interest rate you borrow money at. If you have a really, really good credit rating, you would be AAA, right? And that means you're low risk. It means if somebody lends you money, you're almost always going to pay it back. And so the next time you go out to borrow money, you can borrow at a cheaper interest rate. Now, if you have a really, really low credit rating, that means you are less likely to pay your money back, and somebody would charge you a higher interest rate. So really, if you are borrowing money, you want to have as high a rating as possible. Now, what rating agencies do, like S&P or Fitch or Moody's, is they track the behavior of individual borrowers over time, right? And individual borrowers' credit ratings. And so what this transition matrix shows you is the probability from year to year of starting out as a rated borrower on the y-axis, and then ending up somewhere here on the x-axis. So for example, this part of this matrix here is the probability that a borrower would start out as a AAA, very, very low risk borrower, and end up in the same category. In fact, the whole diagonal section here tells you the probability of, from year to year, nothing changing, right? If you're double B rated, then you stay in double B, and everything off the diagonal shows you the probability of moving away, right? And here you can see the probability of being in default. That's sort of an absorbing state, right? If you eventually default, then the next year you're still going to be in default, right? So just a little bit of vocabulary before we end about Markov chains. Here just describe some additional properties that they can be associated with. So remember that we're dealing with a discrete state space, which means that we're assuming that there's only a couple, maybe not a couple, there could be many different states of the world, but we know that there's a certain number of states of the world that the process can possibly take. So we're going to say that state J is accessible from state I if a system that starts in state I has some non-zero probability, so some probability, of transitioning into state J at some point. Now that does not mean that there has to be a non-zero probability of going directly from state I to state J. It just means that there has to be some chance of, if you're in state I, you eventually end up in state J. Now, if state I is accessible from state J, and state J is accessible from state I, that means you can, if you're in state I, you can get to state J, and if you're in state J, you can get to state I, even if it's not directly. If you can go both ways in this manner, then the Markov chain, we said that these states can communicate with each other. Another property of a special property of a Markov chain, not all Markov chains, but some, is irreducibility. And so that means that all states can communicate with each other. And basically what that means is that no matter what state you're in, you can get to every other state. And then the last property here is transience. So a state I is said to be transient if, given that we start in state I, there's a non-zero probability that we will never return to it. Right? And so there's a couple ways that could happen. You could get into a situation where there are absorbing states, right? So if you have a state I, you could deviate away from it and end up stuck in some sort of state where there's a 100% probability every time that you just stay there, right? Or you could move away from state I and get to a situation where two states don't communicate, so you can get to state J but not go back to state I. If that's not the case, then we say that state I is recurrent, right? A state I is recurrent if there is a 0% probability that we will never return to I, right? If there's always a chance that we can return to I, then we describe it as recurrent. So I think that's all for this one, and I'm going to go put this up on YouTube. Next time we're going to talk